m-fold times acting on y equal to 0 has solution set x to the lambda, natural log of x times x to the lambda, natural log of x to the n minus 1th power, m as in money, m minus 1 x to the lambda power. And I do believe those are linearly independent solutions. Voila, fundamental solution set. Well, for this special case of the Cauchy Euler problem, right? So the question is, how do you factor the Cauchy Euler differential operator, right? At this point in the class, I usually make them listen to Sade's classic smooth operator. There's a song about smooth operators. It's somewhat old now, but I enjoy it. Anyway, is this good? I will go into a waiting pattern. So if we could just factor x, if we could factor L, we'd be done, right? Because if we go back to the argument we gave earlier for constant coefficient case. And also, if you think about it, if we can factor L, we can also do those annihilator method arguments for a new class of functions, right? We could apply the annihilator method whenever we have these kinds of things as forcing functions for the Cauchy Euler problem. There's another way to solve this in terms of a substitution, but I forget. A lot of people like that. It's probably also a good way of thinking about it. It doesn't stick in my mind. I like this way of thinking. All right, so here's the trouble. It is not true that x squared d squared is equal to xd squared, for example. These are not equal. And so in order to factor that, you need basically to take this and you want to convert it to, xd to the nth power plus, say, b1 times xd to the n minus 1 plus plus, b n minus 1 xd plus a0. And that actually kind of gives you a template for what you would want to do, what you'd like to do for other problems in principle. If you can find a single, if you can write the differential operator as a polynomial in some particular differential operator, once you have a polynomial in just one operator, well, one operator commutes with itself. Once you just have it in terms of one operator, then since one operator commutes with itself, you can do algebra on the polynomial without thinking hard about it, right? Or if you could write your differential equation in terms of a couple of operators and those operators commute, you could still get away with it. That's why you can combine Cauchy Euler problems and constant coefficient problems, because I believe the constant coefficient, I think d commutes with xd. I could be wrong about that, but there's more that could be done here. Okay, so the question is, how do you relate these? Well, you just got to work it out pretty much. But if I look at xd quantity squared, right? Acting on a function f, what do I get? I get xd acting on what? xf prime, which gives me what? This gives me x, and then I've got the derivative of x is just 1, so I get an f prime, and then I get plus x f prime prime by product rule, right? But that gives me x f prime plus x squared f prime prime. And then in the other notation, this is xd plus x squared d squared acting on f. Now this holds for all f, right? So therefore we've discovered an operator identity. Xd squared, right, is equal to xd plus x squared d squared. Or more to the point, if I have x squared d squared in my original differential equation, I can trade that for the ever so much more nice xd quantity squared plus xd minus xd. Yeah. So as I think about, solving a particular problem, suppose I wanted to solve x squared y prime prime plus 3xy prime plus a y equals to 0, where this is going to be chosen, I'm going to pick later for our convenience. Okay. Trust me, you'll be happy I put that variable there. So this is x squared d squared, right? So I can trade that for xd quantity squared minus xd, right? Plus 3xd plus a, y equals to 0. And that is exactly what? That's xd squared plus 2 times xd. Oh, I see now that my a should have been 1. Or should it be, what do you think it should be, Daniel? It should be 1. Okay. The reason I choose a equal to 1, of course, is so that I can, yeah. So then we go back to the thing I erased, and we write down y1 is equal to x to the minus 1, and y2 is equal to x to the minus 1 times the natural log of x. And we get the rather exotic homogeneous solution, c1 over x plus c2 natural log of x over x. That's something we certainly did not have in our previous world of examples. So Cauchy Euler problems are neat, different, new, and yet we can apply the operator perspective if we do so choose. You won't find this in books, at least not books that are written today. Not too much, as far as I've seen. This stuff was much more popular, maybe 1960, 1970, something like that. Like I said, Ravenstein is where I saw some of the genesis of these ideas. Actually, a lot of these things probably come from my brother's students at Rutgers asking him various questions about, could you do constant coefficient, could you do variation, could you do undetermined coefficients for a Cauchy Euler problem? How would you do that? Like he had some student ask that, and it kind of just precipitated a discussion, which eventually led to these examples. But if you think about it, you see what I can do. Here's how I can come up with awful new differential equations. I just take my favorite differential operator, t, some smooth differential operator, right? And I just write down a polynomial in t, all right? Any old polynomial in t, y equals to 0. That gives me a differential equation that at this level of notation I completely know how to work with. And I can write down solutions from factoring the polynomial and solving the factored lower order problems. But then if I work that out, it will give me an absolutely ugly differential equation that I can ask students to solve. Of course I wouldn't do that. That'd be evil. It's supposed to work for you, not against you, right? All right, well that's about all I got for you guys in terms of techniques for solving second order and nth order problems with algebra and factorization. The next weapon at our disposal, and there's some things about applications I just skipped over that you should read. I do test on those at the end of chapter 3. Like I derive a resonance condition for, for a given RLC circuit, what frequency voltage source can you put on it in order to get the maximum steady state response? It's a very fun calculation. At the end of my chapter 3, you'll see it. There's a corresponding question, like if you have a spring mass system, what external force can you put on it of a particular type, say a sinusoidal force, can you put on it for a given amplitude that you get the maximum response? The maximum response would be what's called resonance. Actually, it may or may not be that there exists a maximum response. I have inadvertently assigned problems in the past where there actually was no maximum. The pure resonance is easier to understand. If I have y prime prime plus y equal to, a cosine omega t, omega equals to 1 makes it blow up, and anything else doesn't. So anyway, with that, we will stop this part of the lecture. Next time we'll pick up a power series. Thanks. Yes? Is lunchtime? Oh, you have